Okay, so this PowerPoint is a review of speech acoustics. I also posted that reading within the speech acoustics content area on eCampus. It was already included as one of the supplemental readings, but I was sure to put that in there. I think a combination of reading that and this discussion should help those who haven't had speech science yet. So let's go over the vocal tract anatomy, talk a little bit about some of the different structures, how those structures affect the output of the vocal mechanism. So here you can see all the structures, and of course sound starts here from the lungs through the vocal folds. Now air emanating through the vocal folds could either be let me rephrase that. The vocal folds can either be in vibration or not be in vibration when sound passes through the vocal tract. Okay, so when the vocal folds are in vibration, obviously that's a voice signal, and when the vocal folds are not in vibration, it's a voiceless signal. But here you can see the epiglottis, pharyngeal area, the soft palate or velum. You have the oral cavity, the tongue, teeth, alveolar ridge, the back of the teeth, nasal cavity, hard palate, and so on. Vowels are produced with an open vocal tract, and you'll see that in a bit. Consonants usually are produced with some constriction somewhere along the vocal tract. Nasal sounds in particular, what you have in that situation is where the soft palate opens and allows sound, allows airflow to go through the nasal cavity in addition to the oral cavity. Okay, so when you do that, when it happens, you get an increased volume. There's more, you have resonance in not only the oral cavity, but also the nasal cavity, which creates a lower frequency, what we call nasal murmur. Okay, and we'll go over some of these sounds and which ones fall in what category and so forth. But this is the vocal tract. That's just kind of a quick review of the vocal tract. There's an important concept called the source filter model, and essentially we use this model is used for synthesizing speech, for studying speech output. And essentially what it states is that you have a source, you have a filter, which is the vocal tract, and the linear combination of those two lead to a particular output. So in this case, you have a source, which is a harmonic structure with this as the fundamental, and then X number of harmonics that decrease in intensity afterward. And then you have the filter. And this filter, this is a really important part here. This filter, these peaks in the filter, these are resonance peaks. Okay, so remember from the first chapter we talked about resonance. The vocal tract has certain resonant properties, depending on how the vocal tract is shaped during production, and we'll see that later. But so the vocal tract is the filter, okay? And then you add this to this, and it gives you that. And you can see it's the same harmonic structure, but it has peaks where the filter peaks occurred. So here, here, and here, 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 and there. Okay, so that's the source filter model or source filter theory. It kind of serves as the foundation of speech production, which then also goes into speech perception. So here's a phoneme chart where we have vowels, diphthongs, and consonants. Okay, vowels are broken down into front, central, and back vowels. You've all had phonetics. You should be able to decipher some of those. Diphthongs are like two vowels together. And then your consonant sounds: nasals, semivowels, stops, fricatives, and affricates. Okay, all this stuff is from phonetics. Okay, but when we talk about voice signals, obviously vowels are voiced if produced in a regular way. If they're whispered, then they're obviously not voiced. nasals, here's your nasals, M, N, and G. Your stops. We're going to talk about voice onset time and how voice onset time is a characteristic or a cue provided for these stops. Then you have your fricatives and affricatives. So you have some that are voiced like Z versus an unvoiced like S or Sh, the S or the SH, this sound here. Okay. So it's just a review of some of those. So when we talk about vowels, we categorize them into front, central, and back, and then kind of with the tongue height, high, medium, and low. So where they're produced and how high the tongue is. Okay. Now, we refer to this as the vowel quadrilateral. And you're going to see how changes, I found a good visualization of how changes in the articulatory structure of the mouth, tongue, changes the acoustic output for each vowel. So we refer to, so when we talked about resonant properties in chapter 1, first week of class, when we talk about resonant properties for speech production, for vowels in particular, we talk about formant structure, okay, where this is F1, this is F2, and this is F3, okay. So if you look, let's just take a look, and here you have a particular vowel. You see a pretty open, kind of neutral position for the vowel, and that results in this output where you have resonant peaks or formants, excuse me, that occur in certain spots. So this is more of a central vowel, and then we have E as in heed. You can see produced a lot high in the front. Okay, so E has a low F1, a higher F2, and a high F3 where there's not a big difference. Okay. U, as in pull, has a low F1 and F2, and then a big space, and then a higher F3. So it's because of the way in which the vocal tract is shaped that creates these distinct peaks. Okay. Here's a classic study from Peterson and Barney. I don't know if those of you who've had hearing science talked about this, but this is this is from 1952. This is shortly after they developed the spectrograph, right? The ability to obtain spectrograms, okay? And what these folks did is they recorded different vowels from lots and lots of people. And then they looked at, well, what are the acoustic properties? And are there consistent properties within each vowel? Then they plotted the F1 on the x-axis, and they plotted the F2, or second formant, on the y-axis. There's E, I, right? U. Okay? And so they all had similar patterns. Now, one thing to note is there's a lot of variability. So all of these dots within this ellipsis here were identified as E. And you can see there's a pretty substantial amount of variability. Now, they did this for women, children, men, and children, and there was different values. But this is kind of a general. So I think the important outcome of the Peterson and Barney work was that, number one, it kind of categorized, classified, provided information about what formant structure looks like for vowels. The other thing was it showed a lot of variability in the production, yet people still identified E as E despite having all this variability in F1 and F2, because it goes from like 2,000 to 3,500 and from 200 to 400 for F1. Okay, so formant structure is extremely important for identifying vowels. And again, formants essentially are resonant properties of the vocal tract. So in audiology and hearing science, we use the speech signal a lot when we're testing hearing aids and other types of ventures. And so one topic that comes up a lot is the long-term average speech spectrum. Okay, and essentially what the LTASS is, the long-term average speech spectrum, is they'll record speech from males, females, children, and then they look at the distribution of spectral energy. And as you can see, in speech, there's more spectral energy over here in this low frequency, less in the high frequency regions. It slopes at about 6 dB per octave, and that results from a minus 12 dB per octave decay from the source, but then the vocal tract radiates it by a plus 6, so that's how you come up with the minus 6 dB decrease per octave. Okay, so this shows you an ANSI, but don't worry about that. But this basically shows you talker 1, talker 2. There's a little variability, but the overall shape is what I want you to see. Okay, and if you recorded this from numerous people, it would look somewhere between talker 1 and talker 2. But the point is, in speech, most of the energy is contained below 1,000 hertz. So if I were to kind of mark this area, you got more energy here, less energy as it increases in frequency. Now this is a nonlinear visual because the distance between 200 and 1,000, this is 800. Here the distance between 1,000 and 10,000, which is 9,000 difference. So this is a logarithmic scale. Voice onset time, another important concept that helps us distinguish between bilabial plosives like ba and pa. This is a visual to help you. So it's an acoustic cue that's relevant for understanding speech. So with ba, you have an articulatory closer for both sounds. There's the obstruction, which is when the lips are closed. The voicing starts, which is this blue, the voicing starts earlier for ba than pa, and that essentially gives us the cue and says, hey, this is ba versus pa. Okay, I mean, we're talking on the order of millisecond differences. Okay, so voice onset time is an important cue. There's an important concept called categorical perception, and basically categorical perception is a concept that shows that speech is not perceived as some mix between sounds, right, or some gray area between sounds. It is either, in this case, ba or pa, and let me show you that. So if you have a short voice onset time, right here, minus 20, that means before the opening of the mouth, you have the sound almost 100% ba. Remember, let's go back, right? So it's ba when you have a very short onset time. And essentially, when you have these short onset times, it's ba, 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 ba. And then you get to a point where there's this sharp decrease where it goes from like 10 milliseconds to 30 milliseconds, so about 20 millisecond difference. And then it is no longer ba when it has this longer voice onset time. So the same thing for pa. When it's a short voice onset time, it's never pa. And then as it gets longer, you get this point where it goes from never to 100% pa with longer voice onset times. So essentially what that means is we perceive speech as distinct categories and not some in-between category. Okay, there's a short 20 millisecond time frame where we there might be a few confusions, but not many. It's either this sound or this sound. Okay, and we'll go over this again. All right, well, that's it for the speech acoustics. If there are any questions, please reach out and we will we'll chat about this in class again.